everybody. Thanks for coming out early, relatively early. I'm up here to talk about image capture, and the reason I'm talking about that is I'm the developer side of Halide, and I'm also co-founder of a company in stealth that focuses on ML and some computer vision stuff. And the reason you're probably here is that you've been taking photos using UI image picker controller, and you've been wanting to go a level deeper and get more control. And so you dive into AV Foundation, and immediately you hit the wall against CV pixel format type 420 YP CB CR8 biplanar full range, and you have no idea how to unpack any of that. That's okay. Today, I'm going to help walk you through what that means, and I'm going to be covering a lot in a relatively short amount of time. So even if it washes all over you, I have a few goals when you walk out of here today. Now, one, I want you to understand what's possible as you dive into the lower levels beyond what app or UIKit gives you. So for instance, on the left is a photo that comes straight out of the iPhone's UI image picker controller, what the system will give you. And this photo was taken by Sebastian on an iPhone, and he, on the right side, is the same data processed with different choices. There was not a single Photoshop brush tool applied to this, so this is all just choosing how the system processes the same bits. Two, I want to give you an idea of what you don't know. So you can go on Wikipedia later and really try to absorb in depth a lot of the stuff we're talking about. For instance, a few years ago there was a post where someone took this image, which has these interleaved gray rows in it, and they resized this image to 1/4 of its size in a number of popular image editors, including Photoshop. Now you expect the image on the upper right. In fact, due to a very subtle bug that most engineers run into until they understand these little details, it results on the image in the lower right. And we're going to talk about that later. And finally, I want to make all of this a little less intimidating, and I want you to realize that this is fun. It's kind of like a game like Monument Valley, which isn't about reflexes or grinding. It's about looking at a problem with a different perspective. And I don't know about you, but when I played through Monument Valley, the first one, it took me a while to get through it. With Monument Valley 2, I breezed through it because I was now used to, hey, I'm trying to just look at a problem with a different perspective. And what you'll find is, as you do this more and more and you learn to think of things in different color spaces and different ways of looking at the problem, it becomes easier over time, and you get a nice little dopamine kick when you understand a new concept. Today, we are going to be covering these different sections. We're going to talk briefly about exposure, the act of taking a photo. We're going to talk about how the system processes the values that are taken in when you take the photo. We're going to talk about the complexity of displaying it on screen and a very common optimization when you go to move it around the system or save it in a file. And finally, I'll touch on a few ways you could think about using this in your own apps. So let's talk about exposure. All right, and hopefully this is just a review of how photography works. I'm not going to have you walk out here the next Ansel Adams, but there are a few points that I want to cover that are important specific to the iPhone. So as a brief refresher, you start out with a medium that is sensitive to light, like film. And then you put it inside of a dark place, and you shine a light against that medium with some optics that focus the light onto that image plane. And most importantly, you wear some awesome coattails while doing it. The more light that is exposed to this medium, the brighter the image is going to be. The less light that's collected on the medium, the darker it's going to be. And there's some acceptable range that looks visually pleasing. And so the trick is, how do you control the amount of light that hits that medium over a period of time? And so in a traditional camera, you'd have some kind of curtain that sits in front of it or a shutter that briefly opens for maybe 1/30th of a second, and then it closes so that you have a very limited amount of time. Now, if you're trying to take a photo in a very dark environment, or if you're trying to take a photo of the stars, you might leave that window open for 30 seconds or longer. So that's the third variable. So we have these different variables, these little knobs that you can tune to control the exposure. And there's no right or wrong answer as to what these values should be. It's really about what you're trying to accomplish, and that's the whole art stuff that you'll spend a few years getting an MFA in. So the first variable, and there's just 3, is exposure duration, like I talked about. So the longer it's open, the more light, but you end up with more motion blur. So it's probably not very good if you're trying to take a photo of fast action like at a sports event. The second choice is the sensitivity of the medium that you're using to take the photo. So in traditional photography, you can choose different film stocks that are more or less sensitive to light. So for instance, a common number is ISO 800. And that's pretty sensitive, so if you're like indoors, then you could probably get a decent exposure without having to leave the shutter open for too long. If you're shooting in broad daylight, you'll use a lower number like ISO 100, which is much less sensitive to light, but because it's super bright out, that's good to balance it out. And most importantly, the choice that you make changes the signal-to-noise ratio. So if you choose something that's super sensitive, like ISO 800 or 1600, you end up with a bunch more noise, like the image below, whereas ideally you'd want to have a lower ISO if you're shooting in daylight. If you notice, all of Apple's marketing photos with the iPhone seem to be taking place outdoors during broad daylight, and then they use little light modifiers to control it. The third variable is controlling the size of the aperture that light shines through. Think of it like a pipe. The larger the pipe, the more water you can push through at once. So as you increase or decrease the size of the aperture, due to the way optics work, that will increase or decrease the range that can be in focus at once. So let's say that you take a photo of your friend standing in front of the Washington Monument, and you want both your friend who is 10 feet away to be in focus and the monument in the background to be in focus. You probably want a very small aperture, a very small hole, because that's a huge depth of field. Now, if you're taking a portrait, you probably want something blurry in the background because it's visually pleasing, so you'll choose a larger aperture. And so the numbers go lower as the aperture increases. So like an f1.2 is a huge aperture with a very blurry background, and f11 is a very small aperture, so you'll get more in focus at once. Now the bad news is, and not many people know this till they dive into the APIs, no iPhones can control their aperture. They're all fixed apertures right now. Hopefully just right now. I think there is a Samsung phone out now that has a variable aperture, so who knows what we'll see in fall or in the future. Maybe there are mechanical reasons Apple hasn't incorporated it yet. But for now, to create that wonderful bokeh in the background, you need to accomplish this through software effects, like the computer vision tasks that AV Foundation is doing with dual camera fusion, but we won't get into that today. So really, you only have two variables to play with. And for the most part, unless you're developing a niche app, you should just trust the metering choices that iOS makes for you. They are making reasonable assumptions, like the fact that you're going to be holding your phone in your hand, so it needs to be a minimum shutter so that the natural movement your hand makes while it's trying to hold a phone doesn't cause blur. Now, if you are in a situation where you could guarantee that your users have the phone mounted on like a tripod or in a fixed position, then you can play around with the APIs, so you could do a longer exposure setting so you get less noise. But generally, you're fine using the exposure that the system gives you. And for a lot of what Halide does, we rely on the system metering, and then we might augment it afterwards, but we trust the calculations they're making for consistency. Cool. So let's say that we're taking a photo of my beautiful hairy daughter, June, and it's in perfect exposure, and this is the light that is now going to hit the image sensor. Awesome. If we were to zoom in on that sensor and look at what is actually going on underneath, you might think of it as as having its own pixels or sensors that make up the sensor, each recording different values. But this isn't quite how it is, because this would be as if we could record a tuple of red, green, and blue with each pixel, like you would on a monitor. In fact, sensors cannot record light themselves. The hardware cannot record values. It can only record discrete values of what the sensor is reading between 0 and 1 or whatever the bit range is. Effectively, it can only see in grayscale. So this is the first bit of shenanigans we're going to have to do to extract color information using other means. And this is part of the processing stage, which sort of is hand-wavy and handled for you in the system, but let's spend most of the talk talking about this. And to do that, I want to take a trip back to elementary school. I hope all of you remember this. I hope most of you see the number 74. If not, I've got bad news, but we won't get into that. it's a test for colorblindness. And I don't know if they covered this, but what it's doing is colorblindness, the way it works, is that your eyes have a number of cone cells with 3 different lengths. And the size of these cells in your eyes respond to 3 different wavelengths. The longer cells respond to red, the medium ones are green, and the blue ones, or the small ones, respond to blue. And if you have a deficiency in these cells, then you're missing one of these colors in the spectrum. See, what your brain does is it takes these 3 signals of these 3 colors and mixes it together in your brain to form all the other colors in the spectrum. That's pretty cool. So, what if we were biologically inspired and did the same thing with a sensor? And Bryce Bayer, in the 1970s, came up with this idea, and this is known as a Bayer color filter array. And it is an alternating set of color filters that sit on top of the sensor, only letting in the light of that spectrum, so red, green, and blue, alternating. So each separate pixel reads one separate color value. Believe it or not, this photo was shot on an iPhone. Sebastian shot this, I think, in the Muir Woods. And beautiful, beautiful photo, beautiful color. But if you were to look at the underlying sensor data that was captured at the time, it's reading these separate discrete red, green, and blue values, and we're patching them together in a process known as debayering or demosaicing. Now, the reason I can show you this value, and I'm not really making it up, is that at the time of capture, we stored the raw file, which is in iOS. You can now do this, and on any high-end digital SLR, even consumer ones, they now have the option of, in addition to saving the processed image, you can stash like a dump of the buffer for what was in the sensor at the time, untouched, uninterpreted, the raw value. And usually you're going to be storing it in a file format called DNG, which stands for digital negative. This is an open format that Adobe created years ago and Apple's adopted, so it spits out DNGs. Before this, every camera maker invented their own proprietary format, and it was a nightmare. So, in fact, Adobe later released tools to convert all of these proprietary formats to DNG for free. So, you're probably going to be working with DNG, and I'm going to be, for a lot of the slides as I go through here, making different artistic choices. I'm going to be taking the same DNG file and just processing it differently. So, great. So we've got some red, green, and blue values. So it must be simple as just throwing in like a CG context and writing a loop and just giving this tuple of values, and there you've got color, right? That's color, just red, green, and blue. Well, that's kind of, that means nothing without context. It's like if you ask me where's the bathroom, and I say go down the hall, turn left after 20. What, 20 feet, 20 meters, 20 doors, 20 seconds, what? And if you just have red, green, and blue values without context as to what color space you're dealing with, it means nothing. So this horseshoe shape is the entire visual spectrum that humans can see. That triangle in there is the sRGB color space. Most monitors in the world can only display content in that triangle. In the last few years, Apple has released a different color space, Display P3, which is slightly larger, so it more accurately, it approximates more of the visual spectrum, but there's no device in existence that can display every color in the visible spectrum. So there's this user on Stack Overflow who answered a question, what's the gamut of a raw sensor? What's the range of colors it can display? And it can kind of display all of them. If there's one thing you take away today, the sensors on your camera capture tons more information than we know what to do with. So this user mapped the values from the raw file to where they actually sit on that entire visible spectrum. And as you can see, like especially in that magenta photo below, it falls way out at the edge of the inner triangle, butting up against the visual spectrum. So that horseshoe, the theoretical one, is known as the XYZ color space. It's called a reference color space. It was invented before computers were a thing. It was invented in 1931 by an international organization known as CIE. It's French, so I'm not going to try to butcher the pronunciation, but the translation is the International Commission of Illumination. So if you see CIE in reference to stuff, it's some kind of like standard, you know, almost like ISO, the organization board, but they focus on light. Now, what was useful is later, when you're working with a computer, you're probably working in a more concrete color space, an actual real thing that's easy to do math on. So it'll be converted to something like this very large color space, which is known as ProPhoto. Adobe uses it in its products to do calculations. It still doesn't encompass the entire visual spectrum, but it's close enough. In fact, part of it falls outside to make it easier to calculate some stuff, but it's still outside what any display can work with. And later, we'll sort of shrink it down after we're done working on color and doing calculations so it can actually fit on a display. Cool. But before we do that, before we throw out the information, it's important to make some difficult choices. How many people in the audience think this is pronounced Yanni? And how many people think it's Laurel? I hope everyone remembers this meme. It actually has to do with our visual perception of white balance and the context we get in to determine what is white. If you ever shopped for light bulbs, you'll know that you get to choose between this bluish tinted one, which is daylight light bulbs, and soft one, which is yellow. And don't you wish there was a right one? But there isn't. Because what our eyes are doing is we're using the context in the room, our dominant light source, to determine what white is, and we're dynamically shifting it around depending on the environment. It's crazy. Likewise, though, to figure out where white is in a photo, it's important because we're ultimately going to be displaying on a monitor that has a different white balance. So the long and the short of it is, your camera needs to figure out a source of truth for what white is. And it's not a genius. Maybe with machine learning someday they'll be different. But here, the system decided that this sky at the sunset was this neutral white, which is a pretty reasonable assumption. But it's probably not the brilliant sunset you remember when you took the photo. So here's a couple of different choices where the white balance is a little more red and a little more blue. And I don't know if any are more honest or dishonest, but it's really more of an artistic choice, right? The second choice you have to make is around the tone curve that you're going to apply. So here's sample footage from a high-end video camera. And the default image that you'll get off the sensor is relatively flat, like the image on the left. It's very neutral, which is nice. That also means that nothing's clipped. The highlights are still there. The shadows are still there. Because it's difficult to work with RAW on video cameras because it's like 24 frames a second at 12 megabytes per frame, they tend to opt to record flat images like the one on the left so they have more versatility to edit later. And so the one on the right is where someone in an editing bay decided to pump up the color and give it a little more punch. So the system, if you were to take a photo right off the camera, would look really dull, so you need to apply a tone curve to punch it up a little. And in Apple's docs, they call it boost. So on the left, this is a photo that came straight out of camera, deliberately taken in a bad situation where there is a lot of dynamic range between the foreground and the background. So it's difficult for me to expose June while also keeping the background from being blown out. Now, here's the default processing, where if you notice the trees in the background, you lose a lot of detail. On the right, I chose to process it with a little more flat curve, so the background is preserved, but it loses a little bit of that punch. Now, if you look carefully at her fur, here's one other interesting bit. Noise reduction. And if you've ever done work in Lightroom or photos on the Mac, and you set noise reduction to 0, see, as you increase noise reduction, you usually trade off grain for this sort of painterly effect. Even if you set noise reduction to 0, there's always some noise reduction going on in your image, because what's coming off the sensor is a lot noisier than what you think it is. In fact, the team who works on Affinity Photo, I think it was in a forum post, I couldn't track it down, but they wrote their own RAW processor, and they got complaints from users because when you set noise reduction to 0, it looked really awful. They're like, no, we're doing what you asked for, we're setting it to 0. But even in Apple's frameworks, if you set noise reduction off, it's still doing a little bit. So here, this is a choice of, do you like the painterly look, or I think Sebastian and I both agree that it's kind of cool, that film grain, as you see noise in an image. Oh, cool. All right, so we've taken these artistic choices, and now we have to display it on a screen. This is going to be fun. Because while your camera sensor is natively 10 bits or 12 bits or more, that gives you about 1,024 values at minimum. Again, sensors today have even higher bit depths. Conventional file formats, JPEG and anything you display on the web, is 8-bit, which only gives you 256 steps. And broadcast television has a valid display range that starts around 16 to 235, which that gives you about, or 15 to 235, which gives you 220 steps. That's a lot less than you think it is. So one problem you'll run into, for instance, in color, is even though we worked in ProPhoto, if we were to take this data, which in the earlier steps we're dealing with a half float, which is 16-bit. That's huge. If we go down to 8-bit, we don't have as many steps in between to interpret the color values. So we're going to lose a lot of those steps in between for that gigantic color space, which is kind of wasted because we can't display it on a screen. So here I took a photo from Lightroom and cropped the sky. And it has a nice subtle gradient. And I processed it and then exported it in 2 different color spaces, where I saved the JPEG as sRGB, so it's using only the bits that you it's only using the colors you can actually display on screen. And on the right, I'm keeping it in ProPhoto with that gigantic gamut. And I don't know if you can tell, it's difficult, I don't have control over the projector ahead of time, but there is very subtle banding around around the middle of the right image, the middle upper left. It's very, very subtle, and if you zoomed in, you'd be able to tell. So you run into this problem, and you can get around a bit with dithering, but as you use a color space you don't need, you just don't get that very subtle gradation between the color, and you start seeing artifacts. Cool, so simple solution is, as we're going 16 to 8-bit, we convert it to a color space that we're actually going to display. And on an iPhone today, you should probably be using Display P3. On the web, it's more complicated. Cool, so that's color. But what about brightness? This is another fun problem. So you probably think of a gradient when you create it in Photoshop or Sketch as just being a for loop that goes from 0 to 255, and each one is evenly spaced in between. No. Because of human vision, the top is actually what would happen if you did that. A perceptually uniform gradient is a little different because our eyes are more sensitive to the shadows than the highlights. So we notice the steps earlier in the lower in the shadow range much more than the steps above. But computers are linear. Oh, here you go. So if you're going to, by the way, if you're going to actually create a perceptually uniform one, you'd probably bump the 50% point way up closer to the edge. So computers, though, see things linearly. And you probably can't see it in the slide, so I should have linked that. I think the link still is active on Imgur of the underlying image if you want to look at it at your monitor. But if you were to then encode this linearly, you lose all the important bits in the earlier part. You're having to spread those out, so you see a similar banding effect. You just lose all the details in the shadow where they matter, and you have all these bits on the high end that you don't really need because people can't see it. And of course, if you go to edit the image later, you're going to run into problems. You're like, oh, I want to make it brighter. Well, I effectively clipped all of the shadow content that was right on the edge. Cool. So the solution that people arrived at was the idea of, it's called the gamma curve, one of the scariest words for beginning computer programmers because they have no idea what it is, but it's actually a super simple concept. You can still do all your calculations as if it were linear, but then when you store it in a file format like 8-bit, you apply a function to it to raise up those bits. So you're storing it using a log function to sort of boost the shadows, and then when you go to display it later, you apply the inverse of the function before you show it on screen, so everything looks not super washed out. So in other words, on the left is the image that you think you're actually saving into a CG image context or you're saving to a file. On the right is what's actually going into that file, and then your display or Windows server or whatever is then applying a function to make it darker because we need to preserve all the data in the lower end of bits. You really need to understand gamma. It is a source of crazy subtle bugs, like this one. The problem is, when you're resizing an image, you are going to want to interpolate the surrounding pixels. You're going to like anti-aliasing so you avoid artifacts. So you might perform, say, a simple average of these pixels, but because the numbers are different, your calculations will be subtly off. You think that you're dealing with 0.5 gray, when in fact it's 0.72. You just do a simple average, and you get these subtle differences. And so the gray stripes sort of hit that sweet spot where it just gets totally confused and throws away the image. And again, that person who ran that test found that the vast majority of image editors ran into this bug. Photoshop, for the longest time, it would, when it would composite brush strokes, would use the style in the lower left with those fringes because that was a gamma bug. And then eventually they fixed it, but they added in a legacy mode because people were used to those fringes when they draw brush strokes. All the time you'll see with fonts when they're being anti-aliased, because they're blending it incorrectly, you see weird fringes around the edge. In 3D graphics, when you're doing lighting calculations, it's very common for beginning engineers to be like, everything is so dark. And then they start tuning the lights in the scene, and they end up with something that's better, but never really looks right because the underlying problem was they were doing the gamma calculations incorrectly. They were not converting it to a linear space before they were doing the math. Cool. So please read on gamma for my sake. Great. So next, everything's great, but there's got to be a way to optimize this using human perception. Because if you notice, if you look in the docs, for video buffers you can get back in AV Foundation, there's this property saying available video CV pixel format types, and they recommend using the first format type. They just say it's the most efficient. Now, if you drop in the debugger and see what's being returned, it's in a different file format that isn't RGB, and it's very confusing to work with. And I just want to say, is it worthwhile to take an optimization even though you don't need it, right? We're struggling enough with RGB. Why now add this image conversion stuff? And a lot of people like to throw this quote around, so I made it my goal from now on to try to include this little counter in every one of my talks, because people talk about premature optimization as the root of all evil. They leave out the rest of the paper where he says that in established engineering, 12% improvements, if it's easily obtained, is always worth it. So, and by doing this conversion I'm about to talk about, we're going to save 50% of the memory. That's 50% of the transfer time between the GPU or CPU. This is absolutely worthwhile, and it's not really difficult once you understand the concept. So, right now we're thinking about color in RGB. Well, we could split apart our image into two areas. Luminance, like I did earlier, where I was talking about gamma, so that's just the brightness value, or chroma, which is the color value. Now, if I covered those two images on the left and asked you what is the image on the right, I doubt you'd be able to tell that's a flower, whereas the grayscale image you can almost immediately tell. That's because humans are much more sensitive to shifts in luminance than they are in shifts in chromaticity. Okay? How can we exploit this? Well, by the way, this is why we also have twice as many green filters inside of the array, because luminance carries the most information if you're trying to convert from RGB back to luminance. So it carries the most important information, so let's put all of that there. So how do we exploit this? Well, for starters, we'll convert our image now into luminance in one float, or half float, and then we'll create this Cartesian space which covers the amount of red and the amount of blue. So depending on the coordinates in the space is the color value. It's known as YUV or YCBCR, color blue, color red, and Y stands for luminance. And so if we just provide these two coordinates, we get a different space, different color. But you're saying, wait a minute, you're still dealing with three coordinates. Instead of red, green, and blue, we have Y, U, and V. So where's the optimization? Well, once we split out our image into these separate image planes, we can just resize the color values to 1/4 of their size. And nobody can perceive this in an image. Virtually all JPEGs you see online are throwing away 3/4 of the color information, and you, as a person looking at the screen, cannot tell any difference if you held them side by side. The only time that you want to keep that information around is if you're doing something like color grading, if you're color grading a movie, or because you're going to be pushing and pulling color values if you're doing color correction. So if you're editing it, yes, you want to keep it around, but if it's for display or shipping over the wire, you can throw it away and there's no difference. I'm not going to go over exactly what these numbers mean, They're a ratio that have to do with how much information is thrown away. So when you see someone throwing around the term 444, that means that no color information is thrown away. Every pixel on screen has a corresponding color value to go with luminance. Whereas 420 means that it's subsampling, so you basically got 1/4 of the color values. And the ratios have to do with where you're cutting and throwing out the color. But you'll usually see 420. Cool. It is not difficult to go to RGB. I don't know if anyone here has tried to look at the video buffers coming in through ARKit, but in the docs it says that they're always going to be passed back in YUV format, presumably for optimization. God knows how much stuff they're processing to do all that stuff in real time. So there's no option to return RGB. But they give you this matrix that you can copy pasta into your code, apply the multiplication, boom, you've got RGB back. In AV Foundation, you can ask for buffers in RGB format. But one, you're going to be sending more data over the wire, and two, it's impossible to get buffers back in full 4K video if you're asking for RGB. If you inspect the different pixel formats, there's no full screen 4K video available. You have to do this conversion yourself if you're trying to do fun stuff at 4K. Cool. So, in practice, what does this mean for you? And to tell you the truth, unless you're building a manual camera app, you're not going to find too much value in manual controls. If you can make a guarantee that, again, the phone is mounted in one location, or let's say that you're building an app and it's for recording soccer games or youth soccer games for your kids or whatever, right? You're probably going to want more action in there, like sharp and without motion blur. So you could choose to use the system metering. Once that returns, do the math yourself and figure out how you could compensate shutter speed for ISO or whatever. But most apps probably aren't going to benefit from it. That said, it's also the only way to get the longest exposure time is manually asking for it. You'll never get 1/3 of a second, or I've never been able to trigger it in AV Foundation. And the hardware itself only goes up to 1/3 of a second. I have no idea why. I'm assuming it has to do with heat on the sensor, or I don't know if it's a buffer thing, but you can only get 1/3 of a second with manual controls. If you see in the App Store an app that does like 30-second exposures, what they're really doing is they're taking multiple video frames and in software blending them together. So you're not really getting the full raw image in. So it's complicated. So what's more interesting is working with RAW. On an iPhone 6S and later, you can request RAW from the system as you're taking a photo. You cannot record live video buffers in RAW, maybe someday, years from now, but that's going to be crazy intensive on the system. But so when you take a photo, you can say return a JPEG and at the same time return a RAW image, and then you can pass it through Core Image, and they've written all of the RAW stack for you. It's amazing what they give you for free. And so from there, it's super easy to do what you need to create an image like the one on the right. Now, the problem is that these RAWs are 12 megabytes each, and they don't really compress because the definition of RAW is we're not touching the underlying data. It does what it says on the package. They do some limited lossless compression, but I've also read that there are certain patents that encumber anything really nice around RAW, so it's kind of limited. So you should expect 12 megabytes per photo, although apparently Google Photos has figured out a way to do kind of a lossy RAW, which kind of makes me feel uncomfortable, but you know, it's out there. What's nice is by saving these DNGs, you're now future-proof. So if Apple releases a newer color space, next we're going to HDR and wider color gamut, you can actually take your originals and export them and they still work. They'll take advantage of all the colors that are now available. Actually, I don't think that moved into, all right, that's the next slide. You're going to want to work when you're doing calculations in linear color space. If you're using UIKit, if you're using Core Graphics, they try to abstract all this away for you, but as soon as you start dealing with bytes directly, like if you're using metal, it's not going to hold your hand. You're going to have to do the gamma conversion as you pull values out of the buffer. But they do have a special way of sort of tagging buffers or textures, as they're called in GPU programming. You can tag them saying, I want you to convert this to linear space for me when I pull the value out, and when I assign the value, please convert it back. So it will reduce your errors through the mistakes you made of just forgetting to do, hey, raise this to the 2.2. In fact, in the first version of focus peaking in Halide, I was forgetting to do the gamma conversion, and as soon as I switched over to linear space and the calculations actually worked, it turns out this is a lot more accurate because it's actually reading the contrast better and triggering focus peaking better. So what Apple does for you, not many people know this, but so there's a core image filter to import your raw file. They actually have a special property that you can pass, which is CI input linear space filter. So you can inject your own core image kernel to do calculations in the middle of the image processing pipeline. It's all in linear space. It's all in 16-bit half floats. So if you wanted to perform the most accurate Instagram filter ever that's working the full dynamic range, then you'd want to inject yourself into this stage in the pipeline where everything's just prepared for you, and you can apply whatever effects you want, and then it will move further down the pipeline and everything sort of works. Otherwise, you have to be very careful with how you configure the core image pipeline so that every step is in 16 bits, and it's very error prone. Cool. When you are working with YUV, it is highly encouraged. I will admit the first version of Halide, I went with RGB because I'm like, I don't want to write more shaders. And we're going to be moving back over to YUV because in order to do interesting stuff at full 4K, we just have to. So, if you're just starting out, sure, ask for RGB while you're experimenting, but the right thing to do is use YUV wherever you can. That said, if you're just doing something like a histogram where you're just trying to measure the luminance values, there's no need to do any conversion. It's already set aside for you in a separate image plane, so that's one optimization. You need to do it with your, when you're working with 4K video. And show of hands, how many people here are interested in doing anything with Vision or Core ML? Okay, maybe the majority. Be very careful. Read the fine print when you're working with core image models for what the color formats are, what the orientations are. It is very easy, for instance, to export in RGB when the model is expecting BGR. So let's say you have an image recognizer that's supposed to say, is this a cat? Well, if you mess up the colors and they're in the wrong order, it will fail because like that blue thing isn't that orange cat. No, it's not that. And it's completely silent, and you'll pull the hair out of your head for hours trying to figure out what's wrong, and it's a matter of going from one color format to another. Cool. So, KCV, pixel format type, 420, YP-CBCR8 biplanar full range. 420 means 420 subsampled. YP-CBCR, YUV space means it's YUV and not RGB. 8-bit means, or 8 means it's 8-bit. Biplanar means that the Y is in one plane, UV are in two planes, like the photo I showed earlier. And full range means it's 0 to 255, as opposed to video range, which is 15 to 230. Cool. So I deliberately set some time aside at the end for any questions. I know that we covered a lot, but does anyone have any questions about anything related to what we covered? I guess I'm the perfect teacher. So, yeah.
So in practice,
Mm-hmm.
from a user, not programmer point of view,
Mm-hmm.
it looks like you've got kind of a stark difference between doing everything with the built-in, saving JPEGs, etc., and as soon as you jump into an app like Halide, which is working in RAW, you have by design a much more do-it-yourself path through, and it's hard to know what set of applications to use in order to have an appropriate amount of capability with the affordances on the iPhone of being able to see your raw files in
Mm-hmm.
the image gallery and text them off somewhere and so forth without losing the corresponding raw so forth. So, and being able to hand them off for storage in a linked but separate
Sure. So the question was, how do you manage a RAW plus JPEG workflow on the iPhone, because it's very tricky to pass two files around, and I don't know if you've dove into it, but there are many mistakes you can make if you're a third-party app, for instance, and this was a source of huge problems for us. We used to only save RAW files to the camera roll, and by default in iOS, if you pulled the images using the Photos API saying, give me an image from this asset, it would pull down a really fuzzy image. So there's all sort of edge case around this. So in this case, that was because, and I might be getting too many into implementation details, but RAW files, because they're so large and slow to work with, they embed a thumbnail image. That's meant for quickly previewing. So if you're going through Finder and quickly going through your images, it loads like a preview that's about 0.5 megapixel, expecting you to, in the background, be loading up the full RAW and processing it. And the actual size of your images are 12 megapixels. And unfortunately, if you use this API, you only get the thumbnail. We would get tons of requests from users like, why are my photos so fuzzy? And it was because they would load the photo in Instagram, which for a photography app doesn't process RAW. And they'd be like, this is super blurry. And for a while, we figured out, well, we can actually ask the system to embed a larger thumbnail, but that didn't really work. And so the first part of the answer to your question, what we ended up solving is, because there are so many users that they hear RAW and they don't quite understand all of the implications, they think that it's a magic make my photos better button, and it does require a lot of understanding. Well, you can only use it in these certain apps. So they'll download the app, and if a user has to know the difference between JPEG and RAW, you're going to lose. So what the system lets you do is, similar to a digital SLR, you can save a primary asset, which we save a processed JPEG. In fact, we save the one from the system right now. I'd love to in the future play with that, maybe develop our own halide look. But we just save what comes through the system there. It's sharp, fine defaults, no worrying about color curves or anything like that. And then there's an alternate asset you can assign called alternate photo, which is the RAW file. So always do that. And to tell you the truth, unless you're developing a manual camera app, the users should not understand anything about that there's a RAW file underneath backing it. I might not even save it to the camera roll if, let me give you one example of an application you'd use this. Let's say you serve real estate photographers, and it's common to take a photo of like a living room with a beautiful view outside. Usually the dynamic range there is so big between the inside and outside that the window's blown out or the living room's too dark. With RAW, you can do like a pseudo HDR and recover a lot of the dynamic range outside. So if I were building a real estate photographer app and I detected through Core ML or whatever that there was a living room shot of the Eiffel Tower in the background, I would use the RAW, try to recover the highlights and dynamic range, and then ultimately upload it to my service. And I might throw away the RAW because you have to ask, is it really worth 12 megabytes of photo as far as your infrastructure and all that? So yeah, so it's very difficult to surface it to the user and almost certainly isn't worth it, although now with Photos on Mac, it does synchronize in the background, so if they are going to go to edit it later, they do have the option of doing that. But yeah, so be very, very, very careful or you'll get tons of support requests. Cool. Any other questions? Yep. Mm-hmm. Surprisingly, no. I was impressed last year. Well, I wouldn't say if there is a lag, it's never deliberate. It's more like I'm sure some engineer didn't make it in time for the last iOS version. So for instance, when they debuted portrait mode 2 years ago, there was no API to do it. In fact, I don't think there was any way to pull in the depth data when they first displayed or released the iPhone 7 Plus. 1 year later, they have a great depth API, so you can get the exact same depth buffers they're getting in. And they released a core image filter that they said, if you just use these values, you're going to get the exact same effect that you get inside the default camera app. Now, when we adopted it, they also gave other levers and knobs that we could use. So if we want to explicitly say, focus this point versus whatever. So they eventually made it to third-party devs, but they still haven't done it. I haven't checked the docs, but to my knowledge, they haven't done it with lighting portrait effects. I don't care. It's not really our bread and butter. But yeah, for the most part, it feels like we're dog-fooding the same APIs that Apple is. There's a separate issue of sometimes they'll use marketing terms that I'm still trying to figure out what they mean by auto HDR, because if you ask 3 people what HDR means, there's very different interpretations. So figuring out exactly what they're doing in the main camera app and hopefully not recreating it, but doing something similar, that involves more figuring out the product side, what they're doing. But for the most part, like, I can't think of anything that they're locking out of users that I don't have confidence that if I file enough radars, that eventually they'll release to us. And actually, going back to the RAW issue, when we first launched the app, one of the sources of RAW not being read was the built-in Photos app. Photos.app would show a blurry photo. And that was like, whoa, really? And after filing some radars, it might have been that they expected us to save 2 files, but we filed some radars, and this year now the built-in photo app reads RAW files. And so we're now going to get to ask ourselves, do we want to still save a separate JPEG? Do we want to save user space? So as long as you file radars and you do it the right way, then they usually will get it out there. Cool. And I think we're all out of time. All right. Oh, awesome. Thanks.